Hello everyone, my name is Sarang Rajendra Khole, working as a assistant professor at WIT Institute IT Department, Solapur. So today's topic is humming codes. Learning outcomes of this topic, students will able to know that how humming codes can identify and correct single bit errors in digital data and enhancing data reliability. So, what is a humming codes? Humming codes is an error correcting code used to ensure data accuracy during transmission. So, whatever data we are transmitting from sender to receiver, that can be errorless. Humming code detects and correct the errors that can occur when data moved from sender to receiver. It adds one extra bit to original data, allowing the systems to detect and correct single bit errors, that is nothing but a redundant error. So data is transferring from sender to receiver. It is as USB. USB means universal serial bus, which is a combination of 010101 format data. So now, what is a redundant bit? Redundant bits are extra binary bits that are generated and added to the data to information for carrying data transfer to ensure that no bits were lost during the data transfer. So, after adding redundant bit, we can ensure with the help of Hamming code that there is no any error in the data, transmitted data. The number of redundant bits can be calculated using following formula. So in the USB data, so there are 0101 combination of data. In that we have formula to calculate the number of redundant bits. The formula is 2 raised to r greater than or equal to m plus r plus 1. Here m is number of bits in input data and r is actually redundant bit, and this is the formula to calculate the redundant bit. Suppose the number of data bits is 7. We have 7 bits of data, 0101 combination of 7 bits data. Then the number of redundant bits can be calculated using this formula 2 raised to r, that can be greater than or equal to 7 plus r plus 1. 7 is the number of data bits, r we have to calculate. Try different values. So consider r is equal to 3. 2 raised to 3 is 8. 8 is greater than or equal to 7 plus 3 plus 1. 7 plus 3 plus 1, it is 11. 8 is greater than or equal to 11, so this condition is getting false. So now put r is equal to 4. 2 raised to 4 is a 16, greater than or equal to 7 plus 4 plus 1. 7 plus 4, 11 plus 1, 12. 16 is greater than or equal to 12. Thus the redundant bits is 4. For the number of data bits, 7 bits data, we can add 4 redundant bits. Okay. Now pause the video and answer the question. Calculate redundant bit. If the number of data bit is 10, then what is the redundant bit? Answer is again 4. If 2 raised to 4, 16 is greater than or equal to, m is nothing but 10. 10 plus 4, 14 plus 1, 15. So 16 is greater than or equal to 15. So answer again 4. Now before moving to Hamming code algorithm, we have to understand the parity bits. There are two types of parity bits, even parity bits and odd parity bits. If number of ones count in odd, means whatever we are transmitting data 1010 USB, in that number of ones count is odd, the parity bit value is set to 1 to make total counts even number. If the total number of ones already even, the parity bit is value is 0. And it is vice versa for odd parity. If number of ones count is even, the parity bit value is set to 1 to make total count 0, to make total count odd number. If the total number of ones already odd, the parity bit value is set to 0. Likewise that we have two types of parity that is even parity and odd parity. Now moving forward, algorithm of Hamming code. Here we have number of steps. First step is write the bit position starting from 1 in binary form, like here is the binary form 1 2 3 4 5 6 7. We have 2 bit position. Step 2, all the bit position that are power of 2 are marked as parity bits. So power of 2 first is a power of 2 raised to 0, that is nothing but 1. So R1 is a parity bit. Now 2 raised to 1, that is a 2. So R2 as a parity bit. 2 raised to 2, that is a 4. R4 as a parity bit. 2 raised to 3, 8. R8 as a parity bit. Next step, all the other bit position marked as a data bits. So remaining, this is 3, 5, 6, 7, 9, 10, 11, all are the data bits. Step 4, each data bit is included unique set of parity bits as determined its bit position in binary form. So there is a unique set, there are many unique set. First set, 1 in the least significant position, 1 in the least significant position. So R1, whenever 1 comes under this least significant position, that are the combinations. 1 is come for 1, 3, 5, 7, 9, 11. All are yellow is a R1 set. Next set, second set, 1 in the second position from the least significant bit. So second position means for R2, 2, 3, 6, 7, 10 and 11 is the second bit position. This is the second set. Next 4 to 7, that is a combination in 1 in third position from the least significant bit. So 1 is in the third position, which is for 4, 5, 6, 7. For and last set, 1 in the fourth position from the least significant bit, that is 8 to 15. Fourth bit 8, 9, 10, 11. In general, each parity bit covers all bits where the bitwise AND of the parity position and the bit position is non-zero. Step 5, since we check the even parity, under Hamming code we have to check even parity. Set parity bit 1 if the total number of 1 is odd, means we have to set even parity. If there are odd number of ones, we have to set parity bit is 1, and it is already even, then we have to set parity bit as a 0. Now determining the position of redundant bit, where we have to put position of redundant bit. As we discussed, it is a power of 2. Second position we have to add parity bit. So 2 raised to 0, which is 1, we have adding parity bit as a D1 at first position. 2 raised to 1, which is a 2, so D2's position. 2 raised to 2, fourth position, and 2 raised to 3, eighth position. Here total number of data bits is 7 and total number of redundant bits is 4, as we have seen already the example, and we have calculated the redundant bit 4. So 4 bits redundant bits plus number of data bits 7, we have created the USB of 11, that is universal bus, serial bus, which is actually nothing but a data which we are transferring from sender to receiver. Now consider example. Suppose the data to be transmitted, this is the 7-bit data 1011001 from sender to receiver. This bit data, the bits will be placed as follows. So as we have seen, we have added redundant bit at our first position, second position, fourth position and eighth position. So remaining 7 bits data we have placed like this: 1 0 1 1 0 0 1. Okay. Now determining the parity bits. Now we have to put parity bit at the place of R1, R2, R4, R8. Likewise that R1 bit is calculated using parity check and all the bits position whose binary representation includes 1 at least position that we have to see. Now R1, which is a set of 1, 3, 5, 7, 9, 11. We have seen all these things at least position once. So to find out the redundant bit of R1, bit position whose binary representation includes 1 in least significant position. So in least significant position, how many times we have seen 1? We can see here 1, second time 1, third time 1, fourth time 1, fifth time 1 and sixth time 1. So here we can see 6 times 1s, that is nothing but even. So put R1 is equal to 0. Here we have to add, at the position of R1 we have to add 0. Why we have to add 0? Because we have seen that least significant ones in a least significant bit are 6 times. So we check even parity. Now after putting R1 is equal to 0, we have to count the ones of this USB. So instead of R1 we have put here 0. Now we have to calculate total number of ones: 1, 2, 3, 4. So total number of 1 is even number, that is a 4. So the value of R1 parity bit value is 0. Here we have two validations. First we have to check the least position of 1, and after putting the least position even, so R1 is equal to 0. Now we have to calculate from this USB total data number, 7-bit data number. We have to check the number of ones: 1, 2, 3, 4. It is a 4 times, which is nothing but an even number. So the value of R1 parity bit value is 0. Now calculate for R2. R2 bit is calculated using parity check. Same procedure we have to follow. R2 bits 2, 3, 6, 7, 10, 11. Now we have to check the least position of ones. How many times we can see? 1, 2, 3, which is a to find out the redundant bit for R2, we check for even parity. Total number of ones is odd, that is a 1, 2 and 3. Least position is odd. So we put R2 is equal to 1. Here we have to add 1. Why we have to add 1? So we can see the least position of 1 is 3 times. Here 1, 2 and 3. So the number of ones is odd, that's why R2 is equal to 1 we have to add. Total number of ones is odd. After putting 1, we have to check total number of ones in this USB. So R2 is equal to 1. This is second, 2, 3, 4, 5. So total number of 1 is odd. The value of R2 parity bit value is 1. Okay. Same we have to calculate for R4 bit. R4 bit 4 to 7. Now we have to check the least bit, last bit of how many times we can see 1. Here 1, 2. So we check for even parity. Total number of 1 is 2 times. So put R4 is equal to 0. Here we have to add 0. Initially we calculated R1, that was even parity bit 0. Next we calculated R2, that was odd parity, so that's why we have added 1. Now for R4, the number of ones in the least position are 2 times, so which is nothing but even. So put R4 is equal to 0. After putting R4 is equal to 0, we have to check number of 1 in this USB. So 1, 2, 3, 4, 5. So total number of 1 is odd. So R4 parity bit value is 1, because total number of 1 is odd. 1, 2, 3, 4, 5. Next, calculate for R8. R8 bit is calculated using parity check. Same procedure we have to follow. To find out the redundant bit R8, we have to check our least position 1, 2. So this is even. Put R8 is equal to 0. After putting R8 is equal to 0, we have to check for even parity. Total number of 1, 2, 3, 4, 5, 6. It is also even time. So put R8 value, parity bit value is 0. Now when we are trying to send that 7 bits data, actually by adding parity bit, we send the data this value. This 11 bit data we are transferring. So how error detection and correction can be done? Suppose in above example, 6th bit is changed. What was the actual data? This is the actual data we have transferred, and 6th bit, previously it was 0. Now while transmission of during transmission there is noise in the network, and that's why instead of 0 the one number is sent. So how to calculate? First we have to calculate with that number of set. So number of set, we have to check how many number of times one is available in the USB. So first is 0, this is 1, first 1, 2, 3, 4. So here number of 1 are even number, so parity bit is 0. Now for second set we have to check number of ones are available. How many number of ones are available? 1, 2, 3, 4, 5. It is total number of ones are 5. So that's why parity bit is 1. Now the third set, 1, 2, 3. It is also 3 times 1 is available in this set. So here also now parity bit is 1. And for last set, which was R8 set, total number of ones are 2 times 1 and 2. So that's why we have to put here 0. So after calculating total number of ones, we have the binary number 0, 1, 1, 0. Those decimal representation of 6th bit. So that's why contains error that we can correct with the 1 from 0. This is the total procedure of humming code. These all are my references, and thank you. Thank you for watching this video.